Thanks so much. Anyway, I'm here today to give you my perspective on big data, and this agenda really shows in broad strokes what I'm going to be talking about. To begin my talk, Pete Fader of the Wharton School a few months ago described the current state of our industry as suffering from a data fetish. And he said, and I quote, "It's important to have a much broader skill set than just machine learning and database management, but many big data people don't know what they don't know," unquote. And that quote is really a jumping off point for my comments. Now, many of you have probably read and studied the recent McKinsey report on big data. And it's clear that exploiting the value of big data will provide great value to companies, especially in the areas of products, services, customers, quality, and ROI, all areas that companies are focused on marketing and analytics are eager to deliver. The big problem, of course, is the dearth of people who know how to extract the value from big data. And before we examine these issues a little further, let's look for a second at what people mean by big data. Two things we know about big data is that they're expensive to collect and they're difficult to process. And extracting the value is difficult, but I contend that that's not broad or deep enough a definition. When we look at what's out there, the definitions, what you find is one that was developed by Doug Laney, who's now at the Gartner Group. And he's the person that should be credited as the person who coined the 3 V's of variety, volume, and velocity back in 2000. His definition is commonly used, but I think it's lacking in one major respect, and I'm going to get to that in a few moments. To solve for big data, the AMP lab at UC Berkeley has focused on 3 big issues. First, there's algorithms. It's common knowledge that many of the standard algorithms cannot scale to the size of big data, and it requires rewriting those algorithms or sampling the data rather than doing a full analysis. And we also know that while unstructured data are very messy, to use them in any kind of quantitative modeling, unstructured data has to be converted into reliable metrics. Next, machines. Big data processing requires expensive hardware infrastructure like storage, computing, and network resources, which yields a bonanza for companies that sell these services. To cope with the onslaught of data, software technologies like Hadoop and MapReduce have been developed, but we know that these technologies are really good for tasks like storing and searching, but not good at all for doing analytics. And finally, the third need is people. That McKinsey report predicts that by 2018, the U.S. will need 160,000 more people with expertise in statistical methods and data analysis. And we'll also need 1.5 million more data literate managers. And so where is all the activity, news, and buzz around big data happening? Well, I think all the activity and buzz has been focused on solving the 3 V's and not extracting the value in big data. If you look at where all the buzz is happening, I call it's happening in H and H. Hadoop, whose logo is the cute little elephant, and hardware. Software, big iron, H and H. Let me quote Pete Fader about big data again. Pete says, "It reminds me of what was going on 15 years ago with CRM. Back then, the idea was, wow, we can start collecting all of these different transactions and data, and then, oh boy, think of all the predictions we'll be able to make." But if you ask anybody today what comes to mind when you say CRM, you'll hear frustration and disaster and expensive and out of control. CRM turned out to be a great big IT wild goose chase, and I'm afraid we're heading down the same road with big data, unquote. Companies assumed that by putting this new technology in place, all these great fundamental truths about the world would be revealed. In fact, CRM has enabled the sales of lots of hardware and software, but it did not fundamentally change how companies did business. Big data does not equal Hadoop and hardware. And if your business model is to get a bunch of data and run data mining on it, and the secret of increased revenues and profits will be revealed, you're sadly mistaken. I think that we are in danger of believing that a new technology will change how we do business. But instead, we must use these technologies as one of several so as to change our business philosophy and practices rather than seeing the technology as an end in itself. Data-based analytics and decision-making are fundamental to business success, whether your data are big or they are small. And I contend that the fundamental understanding of statistics, multivariate statistics, and Bayesian statistics is the key to database decision-making. Now, some of you may ask, how do we know the world is dominated by the H and H, and not at all by people who have a background in statistics and data analysis? We did a web search a few weeks ago for companies that claim to have a specialty in big data analytics, and we picked the top 20 firms that have been formed in the past 3 or 4 years. And then we looked at the backgrounds of the senior leadership team that was listed on their websites. In total, we identified 91 different people in these 20 firms. Can you guess how many of them had a degree in statistics out of the 91? Well, the answer was 1. Okay, well, how many of these people had a degree in applied math or in statistics? Well, it turns out there were just 5. The remainder of the 91 people with backgrounds in sales and marketing, but the vast majority of the 91 were represented by computer science and engineering. Now, I have nothing personal against computer science or engineers, and we employ several of them, but I contend that these folks are not seeing beyond the 3 V's of big data. Many of you are familiar with the idea of the long tail, and if we sample from the full distribution of events, the long tail teaches us there will be a high likelihood that we will miss important and yet uncommon events. The long tail, combined with big data technology, has given us the opportunity to find and target ever smaller and smaller microgroups with very specific goods and services. The success of Amazon, as a matter of fact, is attributable to this very idea. Now, because it doesn't slip off the tongue so easily, what's another word for the heterogeneity that we find in the long tail? Well, statisticians study variability all the time. It's our bread and butter. We have tools that every person who's ever taken a stat course has heard of, like the analysis of variance. And I argue that we must add a 4th V. Variability, for me, is the most critical V. Understanding variability, which is really about the fundamental differences in relationships across different cuts of your data, is the key to unlocking the value in big data. Yes, you have to have the H&H technologies to get there, but that technology is necessary, but it's not sufficient. And let's talk for a moment then about what I see as the real danger in big data, a danger that statistics and robust analytics can prevent. How many people in our audience know the meaning of the word apophenia? I find that generally not many people do. Well, let me give you a few hints of what it means. This right here is not the President of the United States. It's a piece of toast. This next one is a flower. It's a bit gone by, but it's still a flower. Some people see faces as inanimate objects, but look carefully at that ear. And here's another one. People used to claim to see Elvis in shopping centers. Now they see Michael Jackson reflected on cars. All of these are actual examples of what's called pareidolia, which is a type of apophenia. Pareidolia is the human tendency to perceive faces and features in vague and obscure stimulus. Pareidolia is just one type of apophenia. And apophenia really is what statisticians call the type 1 error. Type 1 errors are false positives, thinking that something is true when it really is not, acting on something when you really should not, thinking you've discovered the truth when it really isn't there, finding a correlation that's big in a sea of data. Let's face it, we are really genetically programmed to make order out of chaos, and that's truly the danger in big data. How can you differentiate a random event from something that is meaningful, sustainable, and something you can make real business advantage out of? And to me, the answer lies in the discipline of statistics. Now, don't just take my word for it. Hal Varian, who's the chief economist at Google, told us that statistics is the next sexy job. We all want to be sexy, don't we? But statistics without theory is just data dredging, strangling the data until it confesses. Behavioral theory is needed to help us structure our problems and develop hypotheses about the way the world works. Statistics helps us to test and evaluate our theories, are right or not. And one of the fundamental tenets of statistics we know is taking a sample of data. But what big data has essentially done is to revolutionize the practice of statistics. We don't need to sample anymore. Statistical models, properly done with the proper software, can scale to big data. And then we can engage in whole population analytics. We can analyze the head and the long tail without taking samples. What are the skills that are needed to analyze big data? Well, Drew Conway of Columbia University devised the diagram that you see, which shows you that subject matter knowledge, math and statistics, and hacking skills are needed. And by hacking skills, he means the ability to parse and process data. And if you have all 3 skills, you can be called a data scientist. Having any tool will not get you there. In fact, the danger zone, the land of apophenia, is characterized by the person with substantive knowledge who knows how to hack and yet knows nothing of statistics. I call this the little Jack Horner syndrome after the famous nursery rhyme, which remember goes, Little Jack Horner sat in a corner eating a Christmas pie. He put in his thumb, pulled out a plum, and said, "What a good boy am I." The person with no knowledge of statistics can happen upon something that looks like a plum, and he can congratulate himself on doing so. But without statistics and theory to help judge whether it's a true finding or just a random occurrence, apophenia is going to rule the day. So what do I see as the statistical tools of the future for big data? For me, it's Bayesian statistics. Bayesian statistics permits us to uncover and quantify all the sources of variability in response or in customer behavior at the level of the individual SKU or the individual consumer. Now, without going into a lot of detail, let me just say about the only thing that Bayesian networks, which a lot of people have heard of, which is a data mining tool, has in common with Bayesian statistics, is the 250-year-old logic of the Reverend Thomas Bayes. Other than that, Bayesian networks, while they are useful, they have nowhere near the power of hierarchical Bayesian statistics. Let me dig a little deeper into that for you. What can we do with Bayesian statistics? Bayesian statistics finds the best fitting coefficients of a complex system of linear or nonlinear equations and can do so often when there is no analytic solution to the system of equations. To do Bayesian statistics, we need the tools of Monte Carlo simulation. And in contrast to Bayesian networks, Bayesian statistics can be used to predict measures that are quantitative or qualitative, including choices, amounts, the timing and frequency of events, and market shares. One of the key benefits is that the analyst can incorporate prior beliefs or knowledge. A simple prior belief is that as price goes up, demand should go down. More complex priors can, of course, be accommodated. Bayesian statistics can deliver results at the most micro level of your data. And essentially, we get a different coefficient for each unit of analysis. This happens in the hierarchical modeling process at what is known as the lower level. Being a multi-level model, hierarchical Bayesian models provide a built-in meta-analysis, essentially the why behind the what. For example, suppose we want to predict consumers' likelihood of purchasing a product based on its price. We would put a negative prior on the lower-level price coefficient that would be generated for each person. The upper model could be used to tell us whether price coefficient differs across demographic groups like age, income, or gender. And both of these relationships, how price affects purchase likelihood and how demographics affect the size of a coefficient, are estimated simultaneously in a hierarchical Bayesian model. Now, when you have many units of analysis, like lots of people or the sales history of a SKU in a store, Bayesian models will do a very, very good job of prediction. But let's say you have a customer who has made only one or two purchases. What on earth can you say about their future behavior? Bayesian statistical models borrow information from others who are similar to that person, using the upper model background information and the lower model purchasing patterns to make a pretty good prediction. And as the person buys more and more, less of this borrowing occurs, and the person's own history will stand alone. Let's look at a quick example of the breadth of modeling done with a hierarchical Bayesian model. What could affect the weekly sales of a SKU in a store? There are many potential effects, from things about the product to traditional and new media and promotions that help drive sales. And in addition, there are things about the store and its environment that could be used in the upper model to help explain the why behind the what. In fact, when using Bayesian statistical models, not only can the inputs be defined as big data, but our outputs are themselves big data. One data set we're working with right now has 4 years of weekly sales from a retailer with over 1,700 stores in a category that has 3,000 SKUs, essentially about 1 billion numbers. Imagine generating over 150,000 coefficients at every one of thousands of Monte Carlo iterations, all in one statistical model. That, by the way, is 3/4 billion coefficients that are being generated. And with all this in mind, why doesn't everybody use hierarchical Bayesian models on big data? Well, first of all, it's relatively new. None of this would have been possible without the recent advances in software and hardware technologies. Second of all, the math is difficult. You need very special people to develop and program the statistical software. And third, the runtimes of these models with ordinary software can be quite long. For example, before we realized that we needed to develop our own software for modeling, some of our analyses were taking days to estimate, and now the same ones take just a few hours or even minutes. Let me give you a quick example of what insights can be gleaned from big data using Bayesian models. In this exhibit, I'm showing you several things. Across the top are 11 different SKUs offered by a food manufacturer. The 4 SKUs on the left with the white background are all large package sizes, and the 7 at the right with green shading are small package sizes. On the left side are shown 3 different channels, drug, food, and mass. And within each of these is displayed the average price of each SKU. Along the bottom in each cell are 7 different time points represented by the time before and the time after 2 successive price increases. Essentially here you're seeing a display of 11 times 3 times 7, or 231 different average prices. Needless to say, this display could be extended further by showing these same 231 prices for each market or geo of interest. Or we might have extended it by looking at different weather conditions, which would multiply the display by a factor of 2 or even by a factor of 100. Now, we all know that these numbers, as you see here, could have been generated pretty much with any analytics package whatsoever. It's really just a bunch of averages. Now I want you to look at the same chart. Here we have calculated 231 combinations, same 231 combinations, but this time we've calculated one Bayesian statistical model, and we are displaying the price elasticity of each SKU in each combination. Note that this is not a display of the average prices, but rather the average responsiveness of the sales to each SKU to changes in price in each of the 231 conditions. These findings, again, can be extended by any of the variables we've included in our upper model or our lower models. As I said earlier, with Bayesian models, not only are inputs big data, but so are the outputs. And so to finish, let me tell you about the pitfalls of big data analytics and how to solve them. The number one danger that I think lurking in big data is variability. To analyze big data, you must be able to explore and explain variance. Second, you must acquire the knowledge and the tools to avoid apophenia. Always be concerned that your brain is not trying to make order out of random events. And to do that, you need theory and statistics. Hal Varian will be glad that you did. With big data, you don't need samples anymore. Sampling can overlook important information when your data are immense. Sampling is the way of the past, and the future, my friends, is in full data set analytics. And I also think the future is in scalable hierarchical Bayesian modeling. I hope I've whetted your appetite a little bit to explore this further. And finally, big data is not Hadoop and hardware. Do not let the IT people take over. We must use big data analytics as an enabler of real business change. Thank you.